Oh, good day. It is 2 minutes till the top of the hour, so we will get started here in just a minute. Thank you. All right, it's the top of the hour. So welcome to our regular webinar series. I am James Okulo, Director of System Planning at eSig, a membership-based nonprofit organization committed to providing our members with objective information, resources, and network opportunities in support of the energy transition. We do this through a number of workshops, tutorials, webinars, blogs, working groups, task force activities, and producing technical resource materials, one of which we will be walking through today. Our workshops and webinars are open to everyone, so please feel free to register at any time at esig.com. Esig.energy rather. If you're new to eSig, I strongly encourage you to follow up with us. You can find us again at www.esig.energy, as well as on LinkedIn, Facebook, and X. Now, before we jump in, let's go over just a few logistics. So please note that the participant lines will be muted during the webinar. And for Q&A, we'll be using Slido at slido.com, slido.com. So please go to slido.com and enter ESIG26 as the event code. The instructions will also be shown on the screen in just a bit here. So we plan to reserve 10 to 15 minutes for Q&A at the end and then conclude at the top of the hour. You will notice on Slido that there is a thumbs up function, and that allows you to support a particular question, and that helps us set priorities on which questions we'll answer first in a somewhat democratic fashion. An email with a link will be provided once the video has been posted. We also plan to provide short responses to unanswered questions after the webinar. So please don't feel afraid to ask your questions through Slido. So getting on to the topic for today. Today's webinar takes up a familiar problem in transmission planning. The key study processes still run in parallel, different assumptions, timelines, decision rules, which can lead to piecemeal fixes instead of a better, more robust, and coordinated solution. And that matters because the need for transmission is growing from multiple directions all at once. On the generation side, the mix is changing, the location is changing. On the load side, growth is rising, becoming more concentrated, and it's certainly creating new pressures on the system. We also continue to see congestion costs at significant levels. Now, all this points to the need for more transmission. Yet over the past decade, transmission expansion seems to be falling behind, with a large share of the development still concentrated in low voltage, shorter lines that are advanced primarily through near-term reliability processes. So the eSig report that was published in December of last year puts forward a straightforward framing. It talks about integrating silos. It talks about broadening the full range of planning drivers and system needs brought into view. And it advocates deepening the analysis as well. And today's webinar specifically is on evaluating more holistic planning framework and asking what changes when long-term planning drivers, planned generation additions, and forecasted load growth are studied in a more unified way rather than through separate channels. And specifically, the presentation will look at a proxy analysis using SPP's proposed CPP process to examine whether better alignment across planning assumptions, timelines, and study scope leads to a clearer view of transmission need and more effective outcomes. We're fortunate to be joined by Ahmed, Rashwan, and Lassetter from Electric Power Engineers, and Ahmed led the task force that put out this report. Ahmed is Vice President of Transmission Planning and Operations at EPE, and Carter is Director of Transmission Planning at Operations at EPE as well. Ahmed and Carter, thank you for joining us today. I'll turn it over to you.
Okay, thank you, James. Pleasure to meet everyone and see everyone here today. And before we dive in, I did want to acknowledge the task force members. This was an extensive effort spanning over 40 members who were engaged on a regular basis, including representation from the ISO, the utility, the technology, and the regulatory community. And so we did have really good context to some of the challenges that we look to tackle through this effort. And so we're really excited about the report they're able to put out. Definitely on the longer side, but we feel it really helped set the context for how to actually implement change within your transmission planning frameworks. So moving ahead, just to a quick introduction. Today our baseline planning practices, they were developed to facilitate incremental and slower changes. We're now experiencing unprecedented changes to the system, both in magnitude and in pace. Driven by growing demands on the system due to load growth, as well as an evolving supply mix, as James noted. All of these are driving the need for generational investments in the power system, and this is across the continent. And so with that in mind, ESA convened the Integrating Transmission Silos Task Force to identify root causes of today's silo planning processes, how those planning processes can be evolved, and a recommended framework for implementation. And it's important to note that the framework that we propose in this initiative is rooted in three main principles: integrate, broaden, and deepen, all of which are aligned with the direction articulated in FERC Order 1920. So moving ahead to an overview of today's practices. Today's processes operate largely in isolation of each other, which lead to silos focusing on a narrow mandate of outcomes, and they rarely look beyond the primary objective of that individual study. So for example, interconnection planning addresses resource additions, but typically only focuses on the minimum upgrades needed, and thus may miss opportunities to address persistent congestion overall. Also, the assumptions that go into these studies are vastly different. You may stress the system to export as much as possible during an interconnection study, whereas in a long-term planning analysis, you may look at looking at load serving capability more focused. So there is a dichotomy actually that exists in how we do these studies. And so as noted, reliability planning ensures compliance with standards, but often omits policy goals or long-term generation and load trends. Economic planning reduces production costs, but may miss flexibility, resilience needs, and depending on the level of granularity for modeling, may miss other more localized needs as well. Asset management replaces equipment without necessarily assessing whether upsizing would deliver broader benefits, and does it integrate with additional work that's going on the system. And at times, public policy is treated as an ad hoc add-on. Similarly, interregional planning is largely developed ad hoc, not necessarily well integrated into existing processes. And finally, operational considerations. As the grid is changing, the demands from the grid continue to increase. Understanding the impacts to operations is critical. And so in today's planning space, there's limited operational considerations included in planning, really identifying the different characteristics of what we're integrating onto the system, any new technologies that are connecting, how those actually impact operations, not just in the planning space, resolving planning problems. So, the question is, why do these silos persist? We recognize that these silos exist. We recognize there's opportunities, but why do they still persist today? A big part of that is cost allocation. With siloed studies, cost allocation is more straightforward. Timelines, and all of these processes have associated timelines on them that don't line up. And if you look at the table that we've included here on this slide, you can see that at times you're looking at 2 to 5 years, 5 to 10 years, 15 to 20. and aligning those assumptions is not necessarily simplistic. Different tools, different models, different assumptions definitely contribute to that siloed nature of the work that we do today, as well as organizational structure. So the organizations that exist today have been built on the planning practices that have existed for decades. And with that, they support the silos that exist. And so in order to actually translate over to a new paradigm when it comes to planning, reinvestment into organizational structure may be required. And lastly, misaligned treatment of uncertainty. When you think of deterministic studies or probabilistic studies, they really look at things with different lenses. And so, how do you bridge that gap overall? And we'll talk about that a little bit more as we go through. So all in all, these all lead to more efficient and redundant projects being selected for construction, which at this time where, time is of the essence and a large spend is about to occur, we really need to shift how we're looking at transmission infrastructure development. So, what are those drivers for change? Congestion is definitely on the rise. 20 billion congestion in 2022, queue backlogs of 2,600 gigawatts, and that's as of end of 2023, likely increased significantly since then. Over 130 gigawatts of data center load projected to be connected by 2030. And DOE's mentioned that some regions actually might need to be doubled in their transmission capacity by 2035. And if we look at the data on the right, which was obtained from FERC Form 1, we're definitely investing more in the grid. But I want to reiterate what James mentioned early on, is that these investments are largely attributed to asset replacements, single purpose upgrades, and don't necessarily address the system needs holistically over an extended planning horizon. So what we proposed was a framework for evolving transmission planning. So to ensure we're meeting the challenge of our time, we need to be purposeful about evolving transmission planning and recognize that more is being expected of the power system than ever before. So when we talk about integrate, we're focusing on processes, data, assumption alignment, and actually consolidation of efforts. So consolidations of actual planning studies to be, more coordinated in how they're executed. And we talk about broadening. So we're expanding the objective of planning, including items like resilience and policy, while capturing more in our modeling to include, extreme weather considerations, real world experiences being looped back into the planning space, interregional coordination, and, evolving system flexibility requirements that we continue to talk about in the industry. Lastly, with Deepen, it's really about increasing the scenarios considered to assess a broad set of potential futures. And this is considering operational impacts, new technology features, and really how to build in portfolios in the future and stage them in, understanding that those uncertainties that we continue to talk about when we're developing projects can be managed through some level of optionality being built into the portfolios. And so with all of this said, we expect this to lead to effective multi-need portfolios. And we'll touch on the difference between multi-need and multi-benefit shortly. And it provides us the ability to understand, what the spectrum of future potential futures looks like and how to develop those least regrets plans and understanding how to put those decision points in for stage investments. Overall, it facilitates us building higher voltage backbones to the system that we desperately need today, based on stacking those values versus those single need transmission infrastructure upgrades. And, when you have a more holistic view on the benefits of transmission investment, when you get in front of the regulators, better project justifications are expected. Swifter interconnection and alignment with broader goals around policy and resiliency are also expected to be positive outcomes. So jumping ahead to integrate. So, what does integrate look like in a little bit more detail? So we talked about timelines and study. Aligning those study timelines, feeding one process into the next is important. Common data. So, it starts with ensuring that your reliability, economic, policy, and interconnection studies have a common starting point. They may stress in different ways, but having a common starting point for the data will lead to convergence in kind of what those assessments are looking at. When we look at scenario development, again, we talked a little bit about that just a moment ago, as ensuring that the scenarios are developed to really look at the spectrum of futures we feel are credible and allowing us to then put together portfolios that address those potential futures. Carrying constraint forwards between study types. So let's think about this in the context of reliability, economic planning, policy planning, interconnection planning as well. So you may end up identifying different sets of upgrades between all three of those different studies, potentially on the same part of the system for different reasons. So having a feedback loop between your studies or a coordination element between your studies can allow for a refinement of those upgrades in a way that can now meet reliability, economic policy, and potentially interconnection related considerations with a few tweaks to the upgrade or an enhancement of the upgrade from being several low voltage upgrades to being a singular ultra high voltage upgrade as well. And restructuring roles within organizations, again, it's really important to ensure that the organizations that exist are set up to support an integrated way of planning. And so moving forward from more fragmented views to a more interactive approach to planning within organizations will lend to those outcomes that we're looking for. And, integration is not necessarily new, but it's been more ad hoc. And so we think of some of the early adopters to some of these integrated elements. We think of ERCOT CREZ enabled 18 gigawatts of wind, 3,600 miles of proactive high voltage transmission being built. MISO's MVP portfolio initially 17 projects at 5.2 billion, focused on policy, reliability, congestion. Definitely early on, SPP's balanced portfolio looked at reliability and economic needs, coordinated regional plans as well. And we look at also CAISO with alignment between some of their major agencies. So between CAISO, CPUC, and CEC, that integrates their resource portfolios and demand forecast into their annual transmission planning. So there's definitely elements of integration that we've seen. Some are more ad hoc with CAISO at this point. It's a regular piece, but definitely want to acknowledge that it's been done. We now want to make this more regular, more purposeful. So jumping ahead to broaden. So really what we're trying to do here is expand why we plan. So setting the objectives that go beyond least cost reliability or congestion relief, and now include public policy, resilience, economic development, flexibility needs, for example. Also broadening what is modeled. So capturing some of the more high impact items like large loads, DERs, extreme weather, planned and unplanned transmission outages, any resilience requirements that may be coming out throughout the industry, and also ensuring that stakeholder engagement is broadened so that we have the right information to go into our scenario development. So that includes state agencies, vertically integrated utilities, ISO RTOs, municipalities, tribes, and neighboring regions all collaborating together. And so what do we feel, from that foundational piece, this looks like in practice? So when you're looking at large loads, there's a way to look at them historically, and there's a way that we've all been advocating to look at them more recently, and certainly in the ESAG world, there's been quite a bit of information published in that regard. So I encourage everyone to take a look at it. But considering operational characteristics, technology uncertainty is very important when it comes to large loads. They're very impactful due to their size and their characteristics. Doing things like including resource adequacy as a transmission planning driver, also very important. We have to acknowledge the role that transmission plays in supporting resource adequacy and ensuring that that is captured in the way we evaluate transmission. We've had unprecedented amounts of billion-dollar disaster events in recent years. And there's been more of a focus on how can the grid be more resilient. So including probabilistic and deterministic approaches to studying system resilience and really answering the call to ensuring that the grid's able to withstand as much as possible in those situations, and if not withstand, recover as quickly as possible as well. Interregional planning is definitely a theme. We have areas that are in surplus and areas that are in a deficit, some of which are quite near to each other. And so we've definitely seen an increased amount of interregional consideration. We've mapped them here on the bottom left with some of the main ones that have been in the industry, and we expect these to become more prevalent as well. But having mechanisms that allow you to integrate interregional considerations into your processes, again, will facilitate these efficient outcomes that we're looking for. And lastly, again, improve policy alignment and scenario diversity with those additional considerations that you're looking at more broadly. With respect to deepen, and I'm going to jump into a couple of slides on this, but really it's expanding and modernizing benefit cost frameworks align with FERC 1920, doing multi-need planning, and we'll talk about that in a moment. So, designing the projects with purpose, not just looking at the value after the fact. Improving modeling of uncertainty and system risk. So as you look at those scenarios, understanding which ones are more probable, how they line up with your expectations, and factoring that into your decision-making criteria. Increasing optionality. So again, handling that uncertainty. When you have so much uncertainty, there's definitely ways to reduce the risk related to them by introducing kind of off ramps in the future into your portfolio development. Understanding that you are expecting to need to make a decision in 3 years. Well, let's put milestones in the plan itself to say in 3 years, we need to make a decision on this element of the plan overall. We don't want to make that decision now because there is uncertainty around that need overall. And then also incorporating operability, as we noted early on, into transmission planning. The system is changing. The technology on the system is changing. The load patterns that we see on the system are changing. Generation and supply mix is changing. So fundamentally, operations is changing. And we have to make sure in the planning time frame, we do what we can to set up operations for success. And for us to do that, we have to better understand what they do on a day-to-day basis and try to project any implications of our work on what they're going to be experiencing in the future. So for multi-need versus single need projects, we're going to give an example of a reliability project that's been identified through a, let's call it a TPL study. On the back end, we can look at the benefits of that project and say, you know what, after we build this project, although it was driven by reliability, it does help some level of renewable integration. It does help with some fuel savings. We did get some resiliency benefits because we added transmission. But it's more after the fact quantification of the benefit rather than the needs driving the decision on the transmission infrastructure. So what we're talking about is different than just a multi-benefit evaluation. It's multi-need design. So understanding when you're recommending transmission, ensuring there is overlap between different considerations. So reliability is one, economics could be another, policy, GI, asset health, whether it's attracting large loads for commercial purposes. What are some of the things that are important when it comes to the design of the system, and ensuring there's some layering between those to maximize the value. And this may end up requiring additional spend, but you will get that additional benefit back once you layer on those pieces. So we expect that your benefit to cost ratio, when you consider multi-need design, will increase substantially relative to single need design projects. So going forward to principles of scenario planning and optionality. So overall scenario development, overall, the idea here is to include base scenarios, but also include some of the elements of uncertainty like public policy, demand growth, and anything else that can be considered a piece that needs to be analyzed for your jurisdiction as part of your development to create that, again, spectrum of potential futures. We want to include things like extreme weather, rapid electrification, different technology cost swings as we're looking into this, and even delayed policy implementation timelines. Those are some of the examples that we've used as drivers for different scenario bases. Now, when we have these scenarios developed and we're looking at the portfolios that we've put forth, we want to use a least regrets, but also probability weighted approach to evaluate those project portfolios. So for example, let's say that we look at 15 different scenarios for the future, and there are common elements of upgrade requirements for those 15 different futures. That's a least regret item to put forth. Now, you may have several other ones that show up in 1 or 2 scenarios, maybe some that show up in 8 to 10. And now you can start to look at that probability weighted element of, okay, so out of these, I'm really sure about the first couple of upgrades, pretty certain also on the other ones, but there is some risk. Those last couple, they only show up in these edge cases. We may not want to push those elements forward. And once you have those portfolios, it could be good to stress test the project benefits under a variety of different futures to ensure that you're not overly dependent on one set of assumptions. So now you've got your scenarios developed, you've got portfolios that have come out of that, but those portfolios can be extensive. And now that we're looking out to a longer planning horizon, you may not need to make a decision on parts of this portfolio immediately. So what are some things that you can do to push back those decisions as far as you can to gain as much certainty as you can? So, planning with optionality is a big part of this. So building to higher voltage or tower class, structuring right-of-ways and land use agreements to support the addition of future circuits, being more modular in design, staging components and having those decision points kind of as you go through. And future proofing, so including HV designs that have grid forming capability, black start, and other beneficial capabilities overall. So to sum up, to try to move from intent to implementation, this is what we've talked about as, being the ideal scenario. You have your coordinated inputs, you integrate your planning functions together, and integration can be common study timelines or can be handoffs between different study types. And the outcome is, a coordinated, efficient, multi-benefit, multi-driver portfolio. And I do want to acknowledge that in the industry, there are elements of this again today that are happening. MISO's LRTP, we'll hear a little bit about CPPs from SPP. The New York public policy transmission need approach, again, California ISO with their MOU with the CPUC and the CEC, PJM building the LT, RTEP, ERCOT's recent 765 backbone studies, and even ISO New England's new LTTP process. So we're definitely seeing movement in this direction. We're encouraged by it, and we're really hoping that over the coming years we'll be able as an industry to tackle the opportunity and build some of these more multi-need portfolios. So if you were going to start somewhere, where should you start? You can definitely combine things in different ways. We're definitely seeing that there's benefits between generator and large load interconnection with long-term planning. Oftentimes, the assumptions in these studies can be in opposite directions, and you can actually drive a need for upgrades that, in one case are exporting, and in another case are importing, and we're going to touch on that in a moment. Asset planning with long-term planning. So like-for-like replacements are a big part of the money that we spend on a regular basis. But we also have these long-term plans that exist in those same areas. Is there a way to repurpose those funds that are being used for asset replacement, build up the system a little bit more to address near-term and long-term needs? And lastly, I know we've harped on this quite a bit today, operations planning as well as planning. Again, acknowledging the grid is changing, understanding that those operational paradigms that we're used to are going to be shifting in the near term as well as in the long term. How can we best prepare for those ahead of time in the planning timeframe? So thank you for your attention on that. Cognizant of time, so I'm going to be passing it over to Carter to pick up on the evaluation of a holistic planning framework. Carter, on to you.
All right, perfect. Thank you, Ahmed. So as discussed in the previous section, a lot of the discussion was with regards to the different transmission planning silos and how they relate to, at times, some disjoint study results. So the intention of what I'll be talking today is about a case study that intends to evaluate the possible benefits of merging some of these currently siloed processes. So I'd first like to also thank SPP directly for being supportive through this process as we developed kind of the case study to demonstrate the benefits relating to the topic we're discussing today, but also extending it to the real world studies and efforts that are being done. And again, providing their valuable insights to help shape this to provide some value as we talk through the study. All right. So for this, we introduced the problem statement. As grid complexity increases, the separation of generation interconnection studies and adjacent transmission planning creates growing risks of misaligned system needs, potentially inefficient solutions, and the challenges facilitating needed generation as we see the load growth. So with this, we looked through the industry for current or planned solutions to address the problem, and we ended up leveraging SPP's proposed and recently approved Consolidated Planning Process, or CPP framework, which is intending to merge some of their study process today, which includes the Definitive Interconnection System Impact Study, or DISIS, which is the study of the interconnection of generation, alongside their Integrated Transmission Planning Process. And this is to help facilitate an improved look at system needs to study the load and the generation together jointly. So with that, some study scope overview. We talked through the development of the scope with SPP a lot, and the development of scope, we look to evaluate currently siloed processes, merging them together, and we came to the conclusion that we would look at the ITP and DISIS separately and then merge them together to draw the conclusions of consolidating them and identifying any benefits of the development of the portfolios that we normally develop separately today. So with that, in addition to what was just mentioned with the looking at them separately as well as joined, we have the development of the grid C mechanism for SPP through the CPP mechanism, and it's the cost sharing between generation and load, which is allowing for more cost certainty for generation to interconnect into the future, especially in these energy-starved regions. That wasn't 100% focused in the study. It's just an aside to note that while we perform the studies with the load and generation together, there needs to be some construct to be able to identify how gen and load will share the costs eventually for the portfolio. And Grid C is a mechanism that SPP has developed to help facilitate that. So a quick background before we jump into the actual case study and the results. We talked through the background of what ITP and DISIS is today. ITP is the integrated transmission planning process they have, which evaluates system needs based on a future look regarding expected generation portfolio, as well as load growth. It's performed on a yearly cadence with the intention of developing an appropriate portfolio to maintain system reliability as well as appropriate rates. And the upgrades are funded by the load. Going on to DISIS, we have a cluster-based study. This is the Definitive Interconnection System Impact Study, which are cluster-based studies where they go through a three-phase process to evaluate the joint impacts of generation within a common cluster. And they're studied in queue, so one cluster after the other. The generation in a certain cluster will be studied together. They will be sitting on top of the latest available models, normally built from the latest available ITP model series. And then as the study is performed, the DISIS customers will be provided insights on what upgrades are found due to the violations. And the DISIS projects or customers will have to fund these upgrades 100%. So they will be on the hook. As Ahmed mentioned in the previous slides, the cost sharing mechanism right now in the DISIS would be it's just the customers that would have to foot the bill. So now we'll talk one more contextual item before moving on to the study results that we saw. We use the DISIS, sample DISIS study results from DISIS 2023 to inform on why we chose DISIS 23 going forward, to inform on how it could benefit from a merging of a process such as CPP. The DISIS 2023 Group 1 project started with 24 projects around 5 gigawatts. At the end of it all, after all the phases and restudies ended, no projects remained in Group 1, no megawatts. So as a result of that, and this is just to inform on the locations in SPP, if you're unaware, we got the groups 1, 2, 3, 4, 5. We're focusing on Group 1. These generators that interconnected in Group 1 originally were influencing significant export issues across Group 1 and Group 2 interfaces. And that resulted in significant rebuilds and new lines across this, totaling over $400 million. And again, as we saw, the projects decided not to proceed because it was too cost prohibitive, and they withdrew. So from that, the study processes may sometimes result in these large bottlenecks that can't be resolved through the DISIS process because the projects themselves would not want to foot the bill for these expensive portfolios. So in this case, we may have to wait until the next ITP process, which will be studying the load growth as well as any generation available to serve it. We may eventually get to the point where we need to build that portfolio out such that it's a build and they will come situation. The generators are waiting for the ITP process to fund the upgrades. And once that happens, then the generators will interconnect. And that can sometimes be detrimental to the overall optimization of what we look for in the system, because the generators themselves actually may be providing relief to the load growth, but it's not found until it's a little too late. So with that, we jump into demonstrating the combined planning benefits, the purpose of the case study, and talking through how we actually evaluated it. So we loosely align with SPP's current processes with ITP and DISIS, and as well as the future CPP construct. We use the normal processes such as the DICES fuel-based dispatch level. This is just the dispatching of the projects, as well as the methodology maintaining how those projects are sunk against the footprint. And we also modify the cases appropriately with load forecast assumptions to provide insight on what we expect to see as we step through kind of that timeline of ITP and DICES. And then we focus on the results from these different scenarios that we look at, identify the portfolios and the large upgrade costs associated to those portfolios, and we compare and contrast against the different cases that we evaluate to inform on the benefits of performing them in a siloed fashion, as well as merging them in some capacity. So we move on to the study models. The study models themselves, we first start out with scenario 1 is an approximate ITP look where we add load to represent when generation in group 1 is close to being at capacity. We have summer peak, winter peak, as well as light load. So we pull on the different peak cases to inform on how much load growth we want to look at to allow the generation to get close to tapping out in group 1. Scenario 2 is a representative DICES look, where we add the DICES 2023 generation cluster projects to provide that how DICES would be evaluated with that starting ITP load profile that we build from scenario 1. We'll skip sensitivity for now. We'll go back to that in a brief second. But then scenario 3 will then take the assumption that the generation in DICES 2023 withdrew, similar to what actually happened in practice. The generation from DICES 2023 withdrew. And we assume in scenario 3 that we have even further load growth on top of it. And you can see the numbers there, but we get it to a point where it's similar to what we see from the 2026 ITP, for instance. So we add more load to this area, and we do not add additional generation from DICES 2023 or other locations. We assume that we did not have generators wanting to proceed forward in group 1. So our scenario 3 is only the additional load look with headroom tapped out because we eventually run out of generation in group 1 to serve all that load. And as a result of that, we do end up needing to import some generation to serve some of that load within group 1. And then scenario 4 is the same load assumption from scenario 3, which is again the scenario 3 ITP look. We add the 2023 DICES generation on top of that assumption, which then allows us to really look at the perspective of if we have load growth from scenario 3 coupled with the DICES 2023 generation request at the same time, we can identify how the merging of looking at generation and load growth together may help identify a more optimal or effective portfolio to facilitate both that load and generation growth. Scenario 4 net sensitivity, as well as scenario 2 sensitivity, is just an additional mechanism that SPP has built in regards to CPP, which is relating to their planned interconnection locations, which is also similar to ITP in their planning sites. But in this case, they screen locations to identify where the interconnection of generation may make the most sense. And those planned interconnection locations are then offered to developing customers to interconnect there. So this sensitivity is a tweak of the DICES 2023 where a few locations are moved to assume that a more optimal location may be leveraging again this specific planned interconnection location process. And we'll talk a little bit more about that, but we extend it to scenario 2 sensitivity just because we want to see an apples to apples look as if we were to do this in the DICES construct today, what would that also look like? So we do the compare and contrast at the end for that as well. So now we go a little deeper into each scenario, and at the end we will combine those and look at the results with relation to the actual portfolio costs. But again, to reiterate, with scenario 1, and this is that moderate load growth model, which represents kind of an ITP lens look, we take the 25 ITP summer peak, winter peak, and light load scenarios, scaling that load in group 1 and having group 1 generation accommodate it. And then after that, we can see that there's sufficient generation to the extent that we are exporting a good amount of generation out of group 1. So there's adequate resources to meet the load in this situation. So with that, we did develop a portfolio for underlying issues identified since we do increase the load to an extent. However, it's not dramatic to the point where it is a limiting factor. So we developed that portfolio and we'll see it later on and how it correlates to the other scenarios, but it wasn't dramatic enough to overlay it since a lot of those were local issues. Moving on to scenario 2, very similar in the sense it's identical to the load profile, but now we add the generation from DICES 2023. As we dispatch it, a significant amount of that generation needs to go somewhere. And since what we're doing is similar to DICES today, a lot of it ends up being exported out of this group 1 area. So as a result, since we're syncing a lot of generation across the SPP footprint as a whole, and we have a lot of this export, we see a good amount of overloads on these regional facilities, as well as some of the local, which isn't explicitly shown in this picture, but understanding we have more violations and a lot of them are related to the seams to get the generation from group 1 out of group 1, since the load growth was adequately supported by the generation that already exists in group 1. And again, this scenario 2 is a good representative of the DICES approach and what we've seen in DICES observations in the past. So this is a DICES look. A sensitivity of this was just us pulling some of the generation around western North Dakota a little further north with relation to kind of where more of the load is and load growth is. But for this, the sensitivity didn't really demonstrate a significant change that you can see pictorially, but some of the local issues did drop, and we'll see that a little later as we go through the combined results and comparisons. So now the fun scenario 3, and the story here is we're going to assume that we have the starting scenario 1 load forecast, and then the generation from DICES 2023 decides that they didn't really like the results that were seen, so they decided to withdraw. We go to scenario 3 and we add even more load on top of it to demonstrate another look at a further out ITP study, where now we have significant load growth, but we don't have the generation to accommodate that load growth at that time. So we've kind of exhausted the generation that exists in group 1, and now we have to pull additional from the south into group 1, and it becomes an importer as a result. So with that, we see a big limiting factor is this line around western North Dakota from a loading perspective. But we do see a good number of voltage issues, whether it's a voltage collapse or just low voltages or non-convergences around these areas. But we do see this scenario 3 being one of the most issue cases compared to the other ones. And we'll go a little further into that as we go through the results and comparing the portfolios. But as we move to scenario 4 and build off of that scenario 3, with the amount of load growth that we have from scenario 3, now we couple it and say, what if we were able to assume that we were studying generation and load growth together and accommodating the load growth with an expected mix of generation that have that opportunity to interconnect to support that. So you can see the export again. We bias it in the opposite direction. It reverses polarity. We were importing from scenario 3. Now we're exporting again. And we do see a good amount of similar issues that we saw from scenario 2 from an export perspective. We also see a similar issue from scenario 3 from the perspective of that northern Dakota area. But we also see a lot of the voltage non-convergence issues go away when we add a lot of these generators in this group 1 to help facilitate that load growth. And then finally, in addition to that, when we implement the sensitivity where we allow a little more targeted locationing of these generators with a planned interconnection location, and that's really just moving some of the generation around the western North Dakota area further north, it takes a lot of the issues away further. In fact, a lot of these regional issues organically drop when we do that as well. So putting all that together, we end up with the portfolios that need to be developed to accommodate the changes and the cases that we developed. Scenario 1, as a reminder, demonstrates that ITP look. We needed about $1.2 billion just to fix the issues within the scenario 1 across the summer, winter, and light load cases. So in order to fix those issues, we get to about $1.2 billion. When you move on to scenario 2, which is the lens through the DICES 2023 customers, which everything would be cost allocated additionally to them, we inflated up to $3.4 billion. So these DICES 2023 customers are having to expend that much money just to interconnect at that location. So we do assume that they withdraw as a result of that to get to scenario 3. But pulling on thread of the scenario 2 sensitivity, which again doesn't exist today in the DICES construct for planned interconnection locations. But if there was an opportunity to better interconnect at better locations, kind of from a screening perspective, you do see a bit of an improvement in the cost. So the overall portfolio cost, if we were to better optimize the location of some of these requests, get us to $2.5 billion. Now, one of the most important takeaways is we get to scenario 3, where we didn't have the additional generation that's interconnecting in group 1 from DICES 2023 when we most need it, which is alongside the load growth in group 1. And as a result, without that generation to help support and accommodate that load growth, we get up to $9.3 billion needed to facilitate all of that load growth. So with that, if we do assume a merging of, if we're looking at the load growth in addition to the generation coming to support and studying them at the same time, we end up with about $3.5 billion worth of portfolio to get both the load and the generation in group 1 together. So again, separately for scenario 3, that's just load growth. It costs $9.3 billion. As of today, how we would execute it, how it would be done, is that $9.3 billion would end up needing to build out, and then the customers after the fact would likely try to interconnect to the system and benefit from that portfolio that's built. And that's why it's a timing issue. The DICES customers may wait until the ITP funds it and then interconnect after the fact. Merging it gets us a more optimal portfolio at 3.5, but also allows us to be more effective in assuming cost estimations between load and generation with that grid C component, which can help optimize the locations of the generation and also allow us to facilitate more generation interconnecting with cost certainty and benefiting from sharing the cost between the load as well as the generation. And again, the tremendous amount of value we go from scenario 3 from 9.3 down to scenario 4, which is 3.5. We would expect generation to be getting a significant discount in how much they would have to pay through the grid C mechanism. And again, in this study, we don't focus on the grid C and how to actually develop the cost right now, because that's still underway on the SPP side. But again, that's just an aside to note that that's an additional item that the customers would benefit from a cost sharing perspective. And finally, the sensitivity, the location of the generation matters. Being able to optimize based on planned interconnection locations can further reduce the end portfolio down to 1.9. So we end up with a portfolio, if we can optimize the locations of generation down to where the growth plus the gen growth can either range from 9.3 all the way down to 1.9 if we allow for kind of the merging of the processes as we see today. This is just a quick visualization of what we just talked about. We have the summer peak load for all the scenarios, where scenarios 1 and 2 around 8 gigawatts, and then 3 and 4 around 11 gigawatts, and then the costs associated to each scenario as well as the sensitivities themselves. So moving forward to some of the takeaways of the results that we've identified and the key components. Like the DICES 2023 cluster showed, the costs may result in being prohibitive to customers wanting to interconnect, so it may lead to high withdrawals. And as a result of this, the portfolio costs get baked into the ITP process, which we saw in scenario 3, which were very high without accompanying GI customer interconnections or generation growth to accommodate or support that load growth itself. Once we balance the load and generation growth that we saw in scenario 4, or the sensitivity, which further improves it, it allows those costs to drop significantly. The portfolio is able to be optimized to an extent that may make it more attractive for generators to interconnect, as well as the ratepayers to be benefiting from this optimized portfolio with the gen and load growth. And then, as we just discussed, the further optimization of those generator sites, depending on how you build that out, can make it better. And finally, We also have the mechanism of unplanned sites where customers don't have to interconnect at those planned sites, which is why some of the results from the DICES 23 customers still showed issues. And in some of those, they may be related to customers that may interconnect at locations deemed as unplanned. And as a result of that, that would be more cost inefficient to the portfolio, but it would be more put on the developers themselves as opposed to the overall benefit of the portfolio developed that we saw through scenario 4, as well as the sensitivity. So a quick summary of what we've talked about, what we saw. With the DICES study process and the ITP study process providing good insights on the portfolios needed, sometimes, unfortunately, we may be a little out of phase with the load forecast, which may be impacting true needs with when the generators are being actually studied. And due to this out of phase studying, we may be in a situation where generation is needed and it's catching up to the actual load growth being studied. So the load growth will facilitate the actual upgrades, and then the generators will catch up and interconnect at that point. But consolidating the generation and the load studies together will help us allow us to identify those joint needs prior to having one or the other facilitate one another. And some final key considerations before we adjourn from this and go into questions. The different study approaches that we've discussed can lead to these different conclusions based on those combined generation impacts. So again, like we talked about the planned sites, that can very greatly impact depending on where you decide to interconnect the generators within a group or within the SPP footprint or in general a footprint. And then studying the load and generation together can reduce the impacts, but the results will remain highly dependent on the assumptions on the scale of the load and generation growth. Sometimes ITP and DICES can be relatively well behaved if the load growth might be very, very slow. But as we see it accelerate, the disjointness becomes more and more amplified, like we saw between the scenario 3 and scenario 4 and scenario 2 that we discussed today. The Grid C framework enables cost sharing for the major upgrades that were originally and historically fully assigned to the DICES customers, but when they decided they did not want to interconnect because of these high costs, in some instances, they would drop until the needs were exposed again in a future ITP study. And that's when they would be funded by the load and fixed, and then the generators would interconnect after the fact. And the one last item, which is just an aside as well, is SPP incorporates also market-based levers in the CPP process to better align outcomes with system needs, potentially reducing export constraints and avoiding costly upgrades. So that's just another item that SPP has introduced in the CPP framework to really hone in on what violations are truly related to the generators that need to be fixed by them, or which ones are appropriately dispatched around from an economic perspective. With that, I can move on to Q&A. I can push it back to you, James, if you'd like. And thanks everyone for the time.
Wonderful. Thank you so much, Carter. Thank you, Ahmed. Ahmed, I'll ask you to come back as well so that we can go over some of the questions. So we'll start with your presentation, Ahmed, and then get into some of the questions that are more specific to what Carter presented. We have about 20 questions, so if we're going to go through all of them, we have what, half a minute rather, to go through each of them. So Ahmed and Carter, you've kind of talked about integrating, broadening, and deepening. Does that entail kind of a wholesale refresh of how we're doing planning right now? And I think, Ahmed, you touched on that. And for regions that are different stages in their planning processes, if there was, one or two things that they were going to start to work on first, what would you recommend? I imagine from Carter's presentation and some of the things you talked about, you have some thoughts on what those would be.
Yeah,
and why.
Absolutely, James. And thanks for the question. I definitely see that there is a need to make a more substantial transformation on how we do things today. Like we said, I think today's framework worked well for incremental change, but we're really dealing with generational change. We're redesigning the system. So essentially, it's a great time to relook at how we determine what is needed for the system more holistically. And if we talk about low-hanging fruit, Carter just went through a great example of how GI and reliability analysis can sometimes be disconnected from each other. And when you look at them more holistically, how you get a more meaningful set of upgrades that facilitate, integrating the generation and the load, without, incurring inordinate costs in opposite directions. So I think that's definitely the first part where I would start, given the amount of generational load that we have interconnecting in the near term. Again, probably because I have a long background in operations, I do believe that we need to focus on operations and planning integration as well. That tie-in is really important to making sure that these portfolios are spec'd out in a way that once they are integrated into real time, they function and they add the values that we expect them to. So those would be probably the two, lower hanging fruit candidates that I would advocate for if someone is starting off at this point.
Thank you. And so maybe to tie your two presentations, and I'm trying to go through the list of questions that we have here. So when thinking about that fragmentation and that disjointed planning that we're currently doing, where is that showing up first, and what's the biggest impact? Is it kind of on the assumptions? Is it on the need identification? Is it on the solution development? And then cost allocation, which I know the report doesn't touch on right now. So where does that show up first, and what is the biggest roadblock? And to Carter specifically, then, is thinking about DICES and ITP. You talked about a sequencing issue there. So which goes first, right? Is it the DICES? Is it the ITP? Uh, is it just a timing issue, or is it also some of the key assumptions that are being used in each one of those? So I apologize, that's kind of a two-part question, right? Where does the fragmentation show up first, which is the most impactful? And then specifically to your presentation, Carter, for DICES and ITP, right? Sequencing or assumptions? If we just aligned assumptions, would that take care of the issues that we're seeing?
Yeah, I think it's kind of a combination of that. Just speaking through kind of the segmentation of these studies, a lot of it, I do think, comes down to the timing impacts and implications, as well as just them being separated organically, because you have different study cadences. For instance, I'm using DICES and ITP since we went through it in the process, but I think it's common across maybe some of the industry as well. But in the case of DICES, you have many phases and people making decisions at different points. And a lot of times those can extend to an extent where an ITP portfolio may be completed at a certain time that actually benefits them, and they want to wait until that happens. So it's a timing thing where you can align the assumptions well, but if it's not consolidated from a study perspective and they're still running in parallel, it's tough to fully align them at any given time without kind of merging them together. And it would still add benefit, to extend one last thing on that. It can still add benefit to align those assumptions between the two, but if you still have them in completely separate buckets, you can still kind of start seeing some divergence between what the portfolios look like.
Thanks. Ahmed, any response to that?
I think Carter nailed it on the head. I think there's temporal aspects and there's common ground up front as well that need to be in place in order to really capture the benefits of integrating the planning processes.
Okay, great, thanks. So one of the other questions is about tools. So we talked about processes, we talked about assumptions. And so the question is, what are the likely near-term opportunities to improve integrated planning? And as an industry, what's our wish list from the tools that we either have or that we would like to have to make this possible?
So I
Yeah,
can speak towards a couple of them if you don't mind, Ahmed, because
sure.
when you perform the analyses, there's always something you want to see to improve the process. And I think one of those comes down to, as you try to merge these processes together, I won't say you're having competing interests, because now that you're ending up with the need to have a portfolio that works out for all. So it's not competing interests of cost allocating this way or that way. But the tools need to be at least flexible as well as intelligent enough to help optimize what those portfolios are. because organically, when you merge these studies together, you're going to see a lot more needs when you perform the analyses, to the extent that you can easily do a one-to-one for some of the obvious upgrades. But once you start looking at holistic solutions like an overlay, a large transmission upgrade to help facilitate all these different, you need a way to be able to have very, very intelligent tools to be able to perform these different permutations to optimize the portfolio, but also tag what is related to what, almost as if this upgrade needs to fix these needs. How can we really bring those together in a way that we're not just saying it fixes it, and my fingers are crossed that if any change happens, we don't blow the portfolio up into the future. So long story short, for the tool itself, I think we need to have something able to consolidate those and be able to develop metrics to identify what these upgrades are really solving and the benefits they're bringing towards the table in that sense.
Yeah, that's a great point, Carter. And maybe one thing I would layer on that in terms of tool functionality is just better communication between our deterministic planning tools and our probabilistic planning tools on the economic side and resource adequacy side. Modeling fundamentals in those are generally quite different. And so you will see things that are not necessarily aligned. So getting better alignment between those two so that you can actually factor in the value of, for example, losing load. So we've talked about this before, where reliability studies, when they identify reliability portfolios, you don't get a good B to C necessarily, but that's because you're not valuing loss load. Once you start to connect these together, start to value loss loading and get that alignment between them, you end up with one cohesive narrative between reliability, economics, as well as resource adequacy.
And Ahmed, I would also say, and you brought up operations, so I wanted to pull a little on that as well, is when we have these portfolios optimized, we don't want to gold plate the system, just assuming if we don't have the gen, what happens, versus if we have the gen, what happens, and looking at the bookends. As we start getting more diverse portfolios, diverse generation, diverse loads into the system, and we develop the portfolios with them, you start seeing that merging between planning and operations, to the extent that we need to have some visibility in a way to merge near-term planning with the operations, so that we're actually coming up with solutions and informing operators from the planning perspective what we see and why we need it, and what generators that are associated to those issues, so they have a better understanding of how they can operate the system appropriately while also leveraging what we already have in place today.
All right, I have 1,000 more questions. I'd really love to spend more time talking about this, and I imagine we'll have plenty more opportunities to continue this conversation. So thank you so much, Carter. Thank you so much, Ahmed, for the wonderful presentation. I've been involved in this, and I'm still learning quite a bit. So thank you so much. Like I said, we will send a recording, an email with a link to the recording of this. We'll also include a link to the report, so you can dig deeper into that. Again, thank you, gentlemen, and thank you to the task force. We had a task force of 40 people representing all the North American ISOs, 10 or so utilities, 40 people in all. A special thank you to SPP for allowing us to work with their system to test out some of the principles that we were putting forward. So thank you again. Have a wonderful rest of your day.
Thank you.